I'm Simeng. This is my final project for the Data Structures and Algorithms course at Berkeley Extension. The topic is Community Detection on Game Similarity Graph. Here is a quick agenda. First, I will talk about the background and why I choose this topic, and then I will go over some community detection methods, focusing on Louvain. Next, I will show the data I used and how I turn it into a graph. After that, I will walk through my code implementation, and finally, I will wrap up with time and space analysis and some practical applications of Louvain. We all know that there are millions of games on Google Play. I work in the game industry and I'm also a player. So from both sides, I see two key problems. As a developer, I want to know how can we make our games easier to be discovered. And as a player, I want to know how do I quickly find games I actually enjoy. So that's why I started thinking, can we uncover the hidden patterns in complex data and group them into meaningful clusters? So the good news is, those problems I mentioned can be solved. Here's what I did. I looked at pages of games on Google Play, and on each page there is a similar game list, and that's how I built the connections. For each game, it can become a node. For example, this is the parent node, and this is the child node. If a game shows up in another game's similar list, then I can add an edge. So I gave the edge a weight 1 over its rank. That means a higher weight means stronger similarity. And why it is undirected. The basic idea here is if I'm similar as you, you are just the same. Now we have this similarity graph, but what we can do with it? That's where community detection comes in. The idea is to find clusters of games that are tightly connected. For example, this is one cluster, and this is another cluster. We can see which games belong to the same group. That's exactly the goal of this project. So the community detection helps us to make sense of this network and organize it into a meaningful cluster. The most straightforward idea is try every possible community combination and compare them. For example, with 4 nodes, we only have 15 arrangements. That's not bad, but with 5 nodes, it's already jumped to 52 arrangements. That's too much. And as we keep adding nodes, the number of the arrangements grow crazy fast. At 15 nodes, there are over 1 billion possible arrangements. So brute force cannot work well. It's just too slow. So we need to find a smarter way to solve it. I looked into different community detection methods, and here is the summary of the information from Wikipedia. Please feel free to pause and take a look if you are interested, but I won't go into detail here. Let me just explain quickly why I choose modularity and why Louvain. So why modularity method? It works great with weighted and undirected graphs. There's no need to guess how many communities there should be, and it is perfect to finding structures in networks. Why Louvain? It's fast and can handle large graphs easily, and it does a great job to maximizing modularity. It has been proven to work well in real-world cases. Now that I have picked the algorithm, let me show you the data I used. All the data was collected from a Google Play similar game list, and I crawled 74 parent games. Each parent linked to 20 to 50 similar games, and overall I got over 1,000 game nodes in my graph. So here is what each row looks like, including the game's name, its rank in the similar list, and its parent's ID and its own ID. Here is what the graph looks like. For each node, here is a game for both the parent game and the child game. The orange nodes are parent game, the blue one is child game, and the size of the nodes represents how many links it has. So for the bigger of the nodes, the more similar games it has. And also you can see that some of the nodes are very central and linked to many others. This structure is what we'll find using Louvain. So how does Louvain works? The Louvain algorithm tries to maximize the the modularity Q, which is the function here, and it's quite hard to understand. The whole process has three main phases. It's also hard to understand at first. But no worries, I will walk through each one step by step with a quick handwritten explanation right after this. This part is to help understand Louvain methodology. So let's start with the first question, how to represent a graph. We use adjacency matrix. Here is a simple graph with only 3 nodes. We put these weights into a matrix like this, and the rows means from, and the columns means to. For example, from the node 0 to node 2, we got weights is 3. Then we add up all the values in the matrix. It turns the double edge weights. We call it 2m. So in this example, 2m is 10. So what is a good community? Here we got 2 graphs. They are exactly the same, but the way they cluster the nodes is different. So which one is better? Obviously, the yellow one is better because inside each community, nodes are highly connected, and between the communities, there are fewer links. For example, here is only 1 and here are 2. We can write this discovery as a fraction. So that means how many edges stay inside communities divided by all the edges in the graph. So the larger fraction means the tighter the community and stronger the structure. But if we put all of the nodes into one big community, this is when the fraction turns to max, and which is 1. And that's not helpful because any graph ends up as just a one big community. So how do we make this work? Just having a big actual fraction isn't enough. It doesn't mean it's better than all other groupings. Instead, we want the fraction to be better than our expectation. So expectation means a random graph baseline. That's where modularity comes in. We take modularity equals to fraction actual minus fraction random baseline. The value ranges from -1 to 1. If it's closer to -1, it is so bad because it cannot even distinguish from random. If it's closer to 1, that's so good because much better than our expectation. We need to figure out what random means. We cut the original graph into steps. There are 2 ends per edge, so in total, we have 2m steps. Then we randomly link them back together, like this. So what the chance that 2 nodes get linked? For one step, the chance to connect to any other step is 1 over 2m minus 1. For nodes u and v, the expected number of edge can be written like this. Then we sum this expectation for all pairs in the same community, and that is the random baseline. We simplify a bit since 2m is much more than 1, so we can drop 1. Now we got everything we need and we're ready to write the full modularity function. Put everything together. After calculating and simplified, we got this, where the first term is the total weight inside a community. The second part is the expected weight from random links. We can also define a shorter name, which is QC. It represents the modularity score of community C. Next, I will explain how Louvain tries to maximize modularity step by step. First, how do we start? In initialization part, each node starts in its own community. That's our starting point, call it Q init. Move to phase 1, local optimization. Now, for each node, we try moving it to one of its neighbors' communities, and we keep moving only if it increases modularity. So let's take this node 0 as an example. We try a few options. First, we can move it to the same community as node 3, get a new modularity Q1, and etc. got to Q2 when 0 moved to the community of 1, and etc. Then we compare all of these Q values with the original init Q, which is we got delta Q, which is the modularity increase, and then we can find the largest delta Q, and we keep the best move. But wait, computing Q for every community for each comparison is very expensive, so here comes to the trick. We can simply find it. We don't need to recompute everything, because moving a node only affects two communities. The one is leaving and the one is entering. We just focus on the gain from joining a new community and the loss from leaving the old one. So our delta Q can be written as delta Q move plus delta Q stay. If the gain is larger than the loss, move to the new node. If not, keep it where it is. Let's break down the formula. Here is an example. The node I is trying to move from community C to community D. We want to see how much we'll gain if move node I to community D and how much we'll lose by leaving its original community C. So first, to calculate the delta move, which is a gain from moving to D. Delta Q move equals to QD after minus QD before. So it's basically how much more internal weights I bring to D minus how much it disturbs the balance inside D. You can see the main term is KIN over 2M. This measures how strong the node I connect to D. And we calculate the delta Q stay, which is the loss from leaving C. So delta Q stay equals to QC after minus QC before. Very similar but reversed. It tells us how much we break the cohesion in C by removing node I. So finally, if the absolute value of delta Q move is larger than the absolute value of delta Q stay, that means a good move. Then we can move node I to D. If not, we are just to keep the node I in C. That's how local optimization works. We do this for every node until no move can improve Q anymore. Move into phase 2, community aggregation. The main idea here is each community becomes a super node, then go back to phase 1. So for two nodes I and J, if the community I equals to community J, that means I and J are the same community. Here, for example, nodes A, B, C are in the same community. They are linked with each other, and C node has self-loop. So when A, B, C are merged into one supernode, the aggregate weights should be equals to doubled all internal edge weights plus self-loop weights. So here in this example, it is 2 times A plus B plus C plus D. And else, if I and J are in different communities, the edge between the supernode needs to be aggregate. So the edge weight equals to total weights of edge between the two different communities. So in this example, the edge weight is A plus B. Combine phase 1 and phase 2 all together. Repeat phase 1 and phase 2 layer by layer. Each layer compresses the graph more. So final result is when no more nodes moves or modularity Q stops growing, that's the final community structure. Here is a brief code implementation. This is the modularity calculation code. The left side is my handwriting derivation of the modularity formula, and the right side is the Python code that implements the same formula. Both of them are subtracting the expected edge weight from the actual edge weight, then summing all node pairs in the same community, like this. And the expect is the degree of node I multiply degree of node J divided by 2m, and the same just as what I have read here. Code implementation for phase 1, modularity optimization. At the left side is a handwritten derivation of how to compute modularity gain or loss when a node moves between communities. The right side is a code implementation of this exact logic, and the key formula here is delta move and delta Q stay. They are directly match the formula I wrote here, and evaluate modularity gain for each possible move can keep the best delta, and that improves the modularity the most. So the logic is same as here. Phase 2, community aggregation. So the left side is a handwritten explanation of how communities are merged into supernodes, depending on whether the nodes are in the same or different communities. In the right side is the corresponding code implementation. Here is replicate of this logic. So if the two nodes belong into the same community, their internal edges become the self-loop in the supernode. If they are belonging to different communities, the edge become the link between supernodes. Full code workflow of the looping algorithm, matching the three main phases already introduced: initialization, phase 1, and phase 2. At the right side is the code implementation of those steps. First, we initialize modularity score. Try to increase the modularity in phase 1 to get the local maximization. If there is no more increase, then we move to phase 2 to aggregate the smaller community into a supernode. And then we go back to phase 1 and phase 2 and phase 1 and etc. until there is no more change in modularity. Then we get the end with the global maximized modularity. Time and space complexity. So first of all, the time complexity. There is no official proof, but I got this from Wikipedia. In most real cases, it runs in about O of m, that's linear with the number of edges. Some says it's around O of n log n, works well even on big networks. In the worst case scenario, it could go up to O of n squared if it only merges one node at a time. The space complexity is pretty efficient. Take about O of n plus m to store nodes and edges. Also need some memory to keep track of communities while merging. Some practical applications of looping algorithm. First, the social network analysis. It can find tight-knit different groups in interest communities, used by platforms like Facebook or Twitter to detect social clusters. Second, App Store recommendations. It can discover app groups based on user behavior or feature similarity. It can help recommend similar apps more effectively. Number 3, marketing and customer segmentation. Group customers based on purchase patterns or behavior, useful for targeting ads and customizing promotions. Thank you. And finally, I generated an animation of the looping iterations of the similar games graph data. I hope you enjoy it.